Okay, so we start with those start at where we left last time. We defined these data vectors. I will not repeat things today because last time I did too much of repetition. This is my vector. Z inverse k x n was 0 0 0 x n minus k, and you have got a band of k zeros. I am also assuming x n equal to 0 for n less than 0. This is called pre-windowed case. We will be doing inner, orthogonal projection and all that, and the inner product will be what? Exponentially weighted inner product, where our forgetting factor lambda was introduced. You remember that was done. I will not repeat all those. Okay. This quantity, this is called the pth order forward prediction error vector at index n, that is taking data up to index n. That data you try to project on the space spanned by past p column vectors, find the error. Okay. So, let me define again W k p n as the span of also you can define the matrix. If you put the columns side by side, you get the matrix. And obviously, k, here we are taking k, minimum k is 1, this is at least one column. Okay. So, z to the power minus k to z to the power minus p, k can be minimum 1. In fact, k we can make k equal to 0 also, because that case also will arise. K equal to 0, k minimum is 0 up to p. The EPFN is what? P 1 P n perpendicular x n. What does it mean? You take the subspace W 1 comma P, 1 comma P comma n, that is the space spanned by Z inverse x n, Z inverse 2 x n dot 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 Z inverse P x n. On that you project x n orthogonally, take the error. Okay. Just quickly, what does it mean actually? That just for once I will do this repetition thing, that is you had this thing Z inverse x, Z inverse 2 x n dot 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 dot, last one is Z inverse P x n, right. These are the columns. You have got x n vector on one hand. You have to find out a set of linear combiner coefficients by which you will combine the columns, take the error, take the norm square of the error. Norm square is not just sum of squares, it is a weighted sum of squares, weighted by the factor lambda. That is, find the error here. What is the last entry? X n minus something times x n minus 1 coefficient times x n minus 1, from here x n minus 2. You follow, na? This column last entry will be x n minus 1, this column last entry will be x n minus 2, this column last entry will be x n minus p. You are linearly combining them, x n minus that. Similarly, at x n minus 1, difference between x n minus 1 and a combination linear combination of the past p samples, again at n minus 2, n minus 2, all that. So, we are finding out those errors, squaring up and adding. Normally, it is just sum of square, which is a good good estimate of the mean square error, prediction error, but here we make it, in order to make it adaptive, we make it exponentially weighted, that is last error, last component of the error, if you call it, just square up. Then last but 1 square up multiplied by lambda, last but 2 error square up multiplied by lambda square dot dot dot, the topmost one square up multiplied by lambda to the power n, add all of them. There is a more general norm expression, when that also for large n gives rise to a good estimate of the mean square error, because averaging is taking place, mean square error. Okay. So, when I do this projection, basically these are the steps that are involved. Here you are not taking just the last entry x n, taking it as a random variable and combining them in terms of random variable, as we did that time previously, where each random variable is treated as a vector. We use the correlation and all that. So, just x n was orthogonally projected on the space spanned by the random variables x n minus 1 to x n minus p. Here it is not, these are only data samples. So, first column, when it is x n, it is the data sample for random variable x n minus 1, it is the data sample for random variable x n minus 2 dot dot dot. At index n minus 1, here is the data sample for x n, this, here is the data sample for, one step past, the random variable which is, passed by 1 index, they passed by 2 index, like that. Here at various indices, you are finding out the error, numerical value, square them up, adding with the weighting factor and minimizing that. Those combined coefficients for large number of rows will indeed converge on the optimal ones. All this we have seen. This is the meaning of this. Okay. Another thing is, even though we write EPFN, we will be basically interested in the last component of the vector, because that is the current component. Current index n, you are combining them, you are using data, past data also, so that the sum of square is a better sum of square, and you are minimizing that, so that you get a better estimate of those combiner coefficient. Using them, you are combining them, you get, and then take the error, you get an error vector. Okay. This is a better estimate of the error vector, because you are using better estimate of the combiner coefficients. But again, in that I am not any more interested in the past values of that error, for prediction error, only the current index. So, last component is important. So, I introduced a vector, remember pi n, I called it pinning vector. Pi n was a column vector, all the elements were 0, only last element was 1. So, pi n transpose times any error vector will be the last component, and that we can denote as EPFN n, isn't it? But why use 2 n? We can use our intelligence just to live with 1 n only. This n means what? We have computed error vector, pth order forward representation error vector by taking data up to nth index. That error vector nth component. But since I will be only using the last component, I can as well deal with that is I will not be using EPFN comma a bracket n minus 2, n minus 3, I will not be using those kind of things. So, you can make it more compact, just this. I am dropping this index n, but its meaning is there. Whenever I write this, it means I am taking data up to index n, finding out the error vector, then taking the last component. Okay. And it is nothing but pi transpose n EPFN. Okay. Similarly, we have got the backward prediction error vector, that is, first let me write down 0 p minus 1, sorry, in this case this will start at z minus 0 1 go up to p minus 1, and instead of this we have got this vector I am orthogonally projected on the space spanned by these columns. Last entry will be here what? X n minus p, and the last entries of these columns will be what? X n minus 1, x n minus 2 up to x n minus p plus 1. So, p future terms, they are combined, the error is taken. Again at index n minus 1, p future terms are combined, error is taken, like that, and those errors are squared, summed with a weighting factor, and then minimized. For large number of samples, it will converge on the optimal backward prediction coefficients. Okay. So, mathematically this is this p 0 to p minus 1, 0 to p minus at index n. So, these two components. Suppose these are given, these vectors are known. In fact, I will be only bothered about lattice recursion that involves the samples, last sample, okay, not the entire vector, but I will derive the recursions first in terms of the vector and then just take the last component. Recursions first will be derived in terms of the total vector, and then I am bothered about the last component, just take out the last component. That is how it will be done. By the way, one thing I mentioned here, EPFN, you see it is a sequence, error sequence. If I give you EPFN, EPFN minus 1, EPFN minus 2, that is the sequence. This sequence will be meaning what? EPFN, that is how I will be generating the sequence. That means, I am taking data up to nth index, then finding out the prediction error vector, then taking the nth component. Next time, I mean if I delay it, the delayed component will be APF n minus 1. Its physical meaning will be what? I am taking data up to index n minus 1, taking a prediction error vector whose length will be 1 less than the previous one, because I am taking data up to n minus, and then taking the last component of that. Then if I delay it further EPF n minus 2, that will mean I am taking data, that is I am taking that estimation process where I am taking data up to n minus 2th index, then finding out the prediction error vector, then taking its last component. That way, please understand this line of reasoning. Okay. Data is to be taken up to that index, and then an estimation is to be performed by orthogonal projection, error has to be obtained, and then take the last component. We will be generating this sequence EPFN, EPFN minus 1, EPF minus 2. I am dropping this index, that is why this confusion might come. This always indicates you are taking data up to which index. Okay. Anyway, now we are giving EPFN and EPBN. I want to find out the same for p plus 1th order. Our procedure will be same as we did in the case of stochastic lattice, but everywhere there will be some finer things which we need to touch upon. Okay. So, suppose I want to find out EP plus 1 Fn. This I have to find out. For this, what is the space? W1 p plus 1 n, is it? Here I had W1 p n, Z inverse 1 x n, Z inverse p x n, p past terms, p past columns. See it that way, p past columns. Now, I am interested in p plus 1th order. So, Z inverse 1 up to Z inverse p plus 1, isn't it? So, enter that space can be decomposed at W1 p n direct sum, take the last guy. What is the last guy? Z to the power minus within bracket p plus 1 x n. Project that orthogonally on the space W1 comma p n, take the error. So, that is, to start with, let us write like that. Okay. Last guy, Z to the power minus p plus 1 x n, that I am projecting orthogonally on the space spanned by what? This pass on this space, isn't it? That was there was an extra guy. This I am projecting orthogonally on this, taking the error. So, I am taking the orthogonal position error operator here for this space. Let us consider this fellow. Let us consider this fellow in detail now. On one hand, this means what? Okay, I will be considering this. Before that, please observe one thing. We know x n definition we know. Z inverse x n is what? 1 0 and then x n minus 1 vector I can write. X n minus vector starts at x 0 x 1 dot 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 x n minus 1, and a 0. Z inverse 2 x n is actually 0 0, then x 0 it goes to x n minus 2. So, I can write that as 0 and then here Z inverse I can apply. Please see this. So, in general dot 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 okay. Understood? This is simple. This fact. Now, you can see here. Here this means actually projection error. First let me write it as original vector minus the projection in that form. Original vector is this minus the projection. Yeah, question you can ask me. I may have maybe making mistakes anywhere somewhere. Yeah, question. Yeah, this is x n minus 1. Thank you. X n minus 1. Yeah. I am writing like this. Now, Z inverse p plus 1 x n means what? Sorry, x n minus 1. I am always making that mistake. Okay. Correct me if I make these mistakes, I have something in mind while writing something else. I can do that. Minus, again the same vector is here, so I will do the same here also. Same vector is repeated here. Now, this corresponds to what? This projection operator corresponds to what? The orthogonal projection operator for which subspace? Subspace spanned by Z inverse 1 x n to Z inverse p x n. Remember p 1 p n corresponds to what? This is the orthogonal projection operator for W 1 p n, that is span of what? Z inverse 1 x n first, that I can write as 0, there is one vector, then last one, how many? Z 2 minus p. These details are not there, x n minus 1, sorry. Okay. So, that means what is this overall projection? This overall projection means this guy is to be projected on this space. So, you have to find out a set of linear combiners coefficients, so that you linearly combine these columns, take the error between this vector and that error norm square has to be minimized. So, you just square up the individual error terms, add them after weighting them with that, weighing them that by that factor, lambda factor, and then minimize that, right. But remember, as you combine the first column here by the combiner coefficient, you get 0, subtract from this guy, you get 0. So, that term when you square up, it contributes to nothing. Are you following me? That contributes to nothing. So, what you are then bothered about is this, to find the this combiner coefficients. This first column, first row does not matter. You have to find out you have to combine them, so that the difference between this guy and the combined output, combined vector, norm of that difference is 0, minimized. Now the difference is, but that difference vector has always, I mean 0 on top, constant, fixed, because of this 0 here and zeros here. So, when you follow the from the sum of squares, what you get? You are as though you are combining these fellows, you are combining these fellows only, these fellows, subtracting the combined thing from this fellow, and that difference vector you are taking, you are squaring up the error in that each error term in that difference vector, multiply, bringing that lambda and then minimizing. But that is what you do. When do you do that? Suppose you are standing at index n minus, suppose you are standing at index n minus 1, n minus 1 is your current index, you can call it even n prime, you can call n minus 1 to be n prime. So, this is n prime, this is n prime, this is n prime. Okay. Forget out that 0 on top, they are not contributing anything. You will finding out optimal combiner coefficients purely from this lower portion of this column vectors and this lower portion. That is, you combine these guys. No, combine these guys by a set of linear combiner coefficients, subtract that from only this much, that error norm square you minimize, you get the optimal set. By that you linearly combine, you still get back 0. This 0 and this combined 0, they match. All right. Now, when you really are doing this much, you are not considering this and you are considering this much, then inverse P x n prime, and you are combining whom? X n prime is the current index, Z inverse x n prime, Z inverse P minus 1 x n prime and Z inverse P x n prime. So, Pth order backward prediction starting at, I mean standing at index n prime, isn't it? Are you getting me? Pth order backward prediction, because you minimize that error, na? You are combining this part, taking the error and minimizing, you will get that those coefficients which when you put for combining will give rise to backward prediction, Pth order backward prediction. It is not as easy as that lattice we did previously. You have to always think about that optimization involved, or projection computation involved. Is this clear? You are combining them, you forget about the top, combining them by a set of coefficients, taking the difference of that from this, n prime is the current index, Z inverse P x n prime means what? What is the last entry? X n prime minus P, and what are the entries here? N prime minus 1 up to n prime minus P plus 1, so on and so forth. So, finding out the errors, squaring up the error, summing them, weighted sum, minimizing. This top fellow you forget, but that is what you do in that Pth order backward prediction computation. Just index instead of n, it is n prime, right. So, that means what will be this projection? Top will be 0, but this part will give rise to what? Pth order backward prediction error vector for index n prime, which is n minus 1. Okay. That means this thing will give rise to what? This is as it is. You can even call it x n prime if you want, n minus 1. Minus this 0 remains as it is, because when you linearly combine the columns, every column has a 0 on top. So, combined output also 0, isn't it? So, that is 0, and before that you get P 0 P p minus 1. Thank you very much. You are understanding. N prime okay. Now you subtract 0 minus 0 is 0 and this is this vector minus here also you see this vector minus projection. So, the corresponding error, isn't it? This 0 does not contribute anything, projecting also you get 0. So, 0 minus 0 0 and is z minus z to the power minus p x n prime original vector and here is a projection, backward projection. Okay. So, that means this becomes simply error. Now, instead of n prime I am bringing back n minus 1. And this error is by our definition E p terms p future 0 to p minus 1. So, p backward projection b index n minus 1. Okay. So, that means simply take the pth order backward projection error at index n minus 1, append a 0 on top. This kind of vectors I denote by this way E tilde b p n minus 1. This means first you remove the tilde, take the vector and then add one 0 on top, call it. Otherwise, every time I have to draw a vector like this. Just to get rid of that hassle, I am just giving it a name. Okay. So, let us come back here. We have to find out this p plus 1th order forward projection error vector. So, this overall subspace was decomposed like this. W 1 p plus 1 n means W 1 p n and the last guy this fellow was projected orthogonally taking the error, but that error is this error is this. Okay. So, that means I can now easily derive x n is to be projected orthogonally on this space taking the error, that means project on this, take the error minus projection along this. I am taking error, that is what I am saying. Otherwise, projection means project here plus project here, then you are computing projection error. So, subtract that from original x n. So, x n minus the projection here, that will give you one error vector minus another component as we did in the lattice case. So, that will be what? X n minus projection of x n on this. You understand now? I will be projecting x n on this means x n on this first plus here, subtract that from x n. So, x n minus this projection here means what? Projection error, pth order, forward projection error. Minus x n and this vector inner product divided by norm square of this this vector into this vector, right. This vector we already found out a name for it, this name, this fellow is of this kind. Remember this, huh? Now, x n I will not show every step, x n inner product with this overall guy. I can repeat this on x n also. You remember that trick I used, x n inner product with this inner product with this vector. If I am computing this, I can repeat this on x n, this operator. Okay. And this guy. You can also call this that name, give it, if you want you can give it you can call it that way, this fellow. And what is this fellow? forward prediction nth index error EPFN EP tilde B n minus 1. Remember it is n minus 1 and tilde. So, 0 on top and that backward prediction error vector pth order index n minus 1, that is taking data up to index n minus 1, their inner product divided by norm square of this fellow. When I do norm square of this fellow, let us instead of viewing it like this, let us consider this fellow, norm square of this. Norm square means using our weighted inner product definition, this entire vector square the last term multiplied by 1, square the last but 1 multiplied by lambda, last but 2 lambda square, like that, and last one 0 square multiplied by lambda to the power n, which makes nothing. So, 1 times this fellow is last entry square up, last but 1 entry of this fellow square up multiplied by lambda dot dot dot, like that. So, it is simply the norm square of this fellow, norm square of this fellow, this total vector is norm square of this much only, because 0 into lambda to the power n makes nothing. Okay. So, when I have norm square of this is simply norm square of this guy. So, simply this, and this fellow I will be calling sigma p into this guy. This guy itself, inner product by norm square of that into this fellow itself. Okay. This overall inner product I will give it a name delta. Please understand one thing, in the case of lattice we used stationarity and then we got a quantity independent of n, and finally, by the recursive mechanism we obtained from the correlation. That is how we constructed the lattice offline. I say offline. Here this quantity is purely data dependent on index n. These are signals. This overall thing is the multiplier. So, lattice filter will be determined by this multiplier coefficient. These are the coefficients, and you see these coefficients are time dependent here. So, we have to have recursive relation, so that their values are changed as new and new data come. This is what we did not do in the ordinary lattice case. That adaptive gradient adaptive lattice is a separate story, forget that. That has a lot of approximations and elimination, all that, so that we are not bothered about. We are doing exact minimization, exact least square error minimization. And here this quantity is purely dependent on n, mind you. I am not making any approximation, no E operator, nothing, no stationarity anywhere. This is what norm squared by taking data of this vector up to index n, up to index n minus 1. When new data comes, I must have the corresponding thing, new norm square. I should have those relations. So, that is how this is a parameter of the filter, some numerator by numerator. Numerator also I will call delta p comma n, depending on n. In the previous lattice case, stochastic lattice case, everything, this inner product was in terms of expectation operator, the entire thing was obtained as in terms of correlations. So, offline you construct the lattice once for all, that is not possible here. I have to have update for this delta. So, this quantity is E p, and by the way, I will not be bothered about this total vector as I told you. I will be taking only the current component. So, now take the last component. This is giving rise to, I should put an index n, then bracket n, but I told you we have the intelligence to understand that, there is no need to put n twice. We will understand, if the moment I put n, it will mean I am taking data up to index n, based on that I am finding out orthogonal projection error, and that error vector nth last component. That is the physical meaning. Okay. That is why I am dropping another index n here, subscript n. So, you take the last component here minus this inner product between this and this fellow and this fellow. I am calling it a name, giving it a delta p n. And here last fellow, please see this, last fellow means this vector, its last component means basically last component of this guy, which is what? Backward prediction error vector, where I have taken data up to index n minus 1, last component n minus 1 is component of that. So, I should have just n minus 1 after this, but I am dropping this index n minus 1, but I will use only once. But this again means it is an error. How it is obtained? By taking data up to n minus 1, then taking the orthogonal projection, appropriate projection, then taking the position error vector, then taking the last component. And these quantities are strictly time dependent. At every time index, I should have their values. I should have adaptive mechanism. I should have recursive relations to obtain this from their past values. And I am doing exact minimization. There is no question of approximation, no E operator, nothing. Okay. Mind you, this is the filtering equation. These are signals only. Parameter, that is multiplier, is this, and the parameter needs to be updated in time, time dependent. So, I have to find out exact update relation, exact some recurrence relation from nth index to n plus 1th index, or at least order update relation. If I know this quantity for pth order, how to go for p plus 1th order and all that. One thing, there is a lot of intricacies here. Again, I come back to this. Here you see actually there is a division. It can so happen that this may lead to division by 0. How? At some time of the lattice, I have to take care of those steps. Suppose it so happened that this guy is already contained in the space here. Suppose how I'll show all those things. You have to be careful. This is contained, and that means if I take the projection of this guy, this guy I am talking of, last guy. This is Z inverse 1 x n up to Z inverse p plus 1 x n. The last fellow is this Z inverse p plus 1 x n. Suppose this is already contained in this space. So, if I project it, I will get back this fellow only, and the error will be 0. Okay. If this guy is already contained in this space, that means these columns will be linearly dependent, because at least one column is contained in the space spanned by the remaining ones. That is manifesting here in this way. This fellow which is given as a, which is contained in this space, if you now project it or take the ortho projection error will be 0 vector, and obviously norm square of the error vector will be 0, and that will manifest here. This is an error vector, isn't it? So, when you just go in blindly in this algorithm, you will find out this is turning out to be 0 at some time. How? When can that happen? We can see now. Consider our matrix. How is our matrix? First one is x n. Suppose I am considering n up to index n equal to 4. So, x 0, sorry, and I am doing forward prediction. That means x 4 is what? X 0 as an example only. I am taking n equal to 4 or n equal to 3, x 3. And what is that matrix? Just a minute. I will put an appropriate figure here. First one is delayed version. Remember x 0, I am assuming x 0 is non-zero. Suppose I take up to this, can you see that these columns are linearly independent? If x of 0 is non-zero, x 0 is a non-zero data, this column linearly independent, because even if you combine these two, you cannot get non-zero quantity here, isn't it? Anyway, if you just this column multiply by C1, multiply by C2, multiply by C3, add C1 x 0 plus 0 plus 0, C1 x 0, if that is 0, C1 has to be 0. If C1 0, then C1 x 1 plus C2 x 0 plus 0 has to be 0, but C1 is already 0, so C2 has to be 0, so on and so forth. This much is no problem. Okay, 3 terms, and this guy is clearly out of, it does not remain in this space, because this has x 0 on top, this has zeros. Even if you combine them, you cannot get the non-zero here. Okay, so you can clearly project it orthogonally on this. You get a projection error, which is non-zero vector. You have a non-zero norm square, all that fine. Suppose I have reached this stage where 0 0 0 has come. Up to this was order 1, p equal to 1, p equal to 2, p equal to 3. Okay. Suppose I want to go for another at this stage at index n equal to 3, n equal to 3 at this index, I want to go up to another order. So, I will have this. Now, I want to project this vector on the space spanned by these 4 columns in that manner, recursive manner. So, I will, if I go like that, I will say the space spanned by the 4 columns is the space spanned by the 3. The direct sum of what? The space spanned by the orthogonal projection error of this vector on the space spanned by the 3. But this is all 0 vector, this is already content here, isn't it? So, that error will be 0. Are you following me? And that is that the error square, the norm square will be 0, and that will immediately manifest that you will have division by 0 problem. But this is bound to happen, because at index, suppose I am doing at index n equal to 3. If I had done it at n equal to 2, you cannot tell me that I cannot go on adding higher orders as long as your index does not grow sufficiently. That will be terrible. That is not an algorithm that can work. Even at index 3, I can go up to order 10, order 11, order 12, order 14, order 20, and all 0 0 0 0 0 0 0 0 columns will come up. Suppose I want to go maximum up to order 20. So, that I have to do for n equal to 0 also, 1 also, 2 also, 3 also, for all n. You remember I told you the number of rows must be greater than or equal to the number of columns. That was a general condition, but in this data structure, the moment you see you have even this equality, because of the zeros presence, you have this problem coming. This comes only with respect to backward prediction. Suppose you have got this space, you have to do forward prediction of this. Suppose you have to do pth order, you have to do backward prediction. Current vector, forget about this, current vector, this column, this column, this column, this column, 4th order. Like here also it was 4th order, this was to be projected on space span by the 4 columns. I had obtained prediction for 3rd order, I was going for 4th order. Here also suppose I want to do 4th order backward prediction. Current vector, 1 delay, 2 delay, 3 delay, 4 delay. So, this guy has to be projected orthogonally on the space spanned by this fellow and these 3 fellows. So, there again you can decompose the entire space as what? Space spanned by these 3 and take this, project orthogonally on the space spanned by these 3, take the error. There I do not have any problem, but this is happily lying outside the space spanned by 3 always, because it is non-zero. This vector does not lie in the space spanned by them. So, there I do not have the problem that error vector is a 0 vector, its norm square is 0 and division by 0 occurs. This occurs only in the, is manifesting this dependence only in the backward prediction error norm. This is bound to happen, mind you, at least for those indices when number of orders is large than the index number, there is number of row is less, because all 0 columns will come up. Are you following me? So, that means my algorithm in the end has to have those mechanisms also by which division by 0 is automatically restricted without affecting the algorithm. I am just telling you, dropping the hint. It is not nowhere near, I mean this adaptive, the stochastic lattice. It is much more trickier, much more challenging. They are the E operator and those absolute things, ideal things, correlation and all, they saved us. Here it is purely data dependent. There is no question of safety using some, abstract E notion. It is purely exact computation everywhere. Okay. So, remember this you take with a pinch of salt, that this division is possible, dividing only when this is possible, that is we are doing an update only when this is non-zero. Okay. So, this was for forward prediction error updating. The same thing we can do for backward prediction, we can quickly do that. And mind you, I am doing it like in the case of stochastic lattice, I did what? I am doing it up to first order. That is from E1 Fn, I am going to E2 Fn, then E3 Fn and all that. Okay. But what is E0 Fn or E0 Bn, 0th order, that will obtain separately. You remember there also I started at E1 F, E1 N F, E2 n f, E3 n f, like that, order recursive. Your starting was E1 n f or E1 n b, okay. But I have to get them from E0 n f, E0 n b. What is E0 n f, E0 b? We will directly see. That is what I did there also. Now comes this thing, backward prediction thing. This you have to find out, and this is equal to what? P0 P the space here is W0 Pn, which is span of z minus 0 xn is xn. Okay. This is same as what? Take the space span of this part, that is W1 Pn, and this guy z inverse 0 means nothing, xn, xn projected on this space, taken the error, that is obviously EP n f. This is very simple here. This part, span of this part is W1 comma P comma n, and then other part is what? Orthogonal decomposition is what? Span of what? Xn, z inverse 0 means nothing, xn projected on this subspace, spanned by these fellows, error. So, that is EPFN. We have just now seen, na, past P samples, past P vectors. So, that means what is this quantity? This guy is to be projected orthogonally, on this, subtracted from this. This guy, this fellow has to be projected on this and on this, and then that has to be subtracted from this fellow only. If you take this and project on this, we have seen it here, we have seen it there, you will get this component. Z to the power minus p plus 1 x n is this, which is 0, and z to the power minus p x n minus 1, which I call n prime, isn't it? And 1 to p was what? Z inverse 1, x n was what? 0, x n minus 1, which is x n prime, dot dot dot. This we did here, this projection we did here. Okay. So, you will get this component when you project this query on this fellow and take the error. Minus this guy, inner product with this, divided by norm square of this into this. But this is what? EPFN in terms of projection is what? P1 comma P comma n f x n. That operator I can work on that also. After all, EPFN is what? EPFN is P1 comma P comma n x n. This is EPFN. So, this operator I can work on this fellow also. I can repeat. Divided by norm square of this, okay. And once again, this is this quantity, this quantity are same, isn't it? P1 Pn, this EP, this, and this is your EPFN. This inner product, or in the other recursion, what inner product we got? those two are same. This inner product and this inner product, they are same. Because real data A comma B, inner product or B, A with B or B with A, they are same. Here they are the two terms where EPFN and EPB n minus 1 tilde. Here it is EPB n minus 1 tilde here, this guy EPFN, inner product is same. This quantity I will name as sigma p n square. So, if I now take the last component, the last component here, I drop this index. Okay. Here I do not have any problem with this division. I told you, because of the data structure here, this error vector will always have, will be non-zero error. You remember the data structure showed x 0, x 1 up to x n is the x n, then Z inverse x n, Z inverse 2 x n and all that. When you project x n on the space spanned by those fellows, x n is never contained in the space spanned by those fellows, those delayed vectors. So, error vector will be always non-zero and norm square. Problem was coming in the backward projection case, the division by 0 thing was coming up. Okay. These two are things. Yeah, sigma f, yeah, okay. I forgot to this sigma f, yeah. And you can also update these two, order update. See, like these are the signals. Signals are no consequence to me. Basically, the filter is constructed by these parameters and the parameters are time dependent. So, every time I have to update them as new and new data come. These fellows can be order updated. If you know them for pth order, you can go for p plus 1th order, is the same way as we did earlier. But then at the very initial stage, when there is no previous order, that time they have to be updated in a time recursive manner. There is a new data come at the very first stage. With the new data, new norm square will be evaluated and that will be order updated. Are you following me? Not following me? From pth order, these two norm square will be updated. You get p plus 1th order value at the same index n. At the same index n, then you by the update, there will be using that update relation I will derive, get the same values for p plus 2th order, so and so. But you then go backward, you come to the very first stage of the lattice, 0th order. That time I cannot go any further stage backward, isn't it? So, that time those quantities will be what? Will be updated. Updated with as new data comes, and as you move from n to n plus 1th index or maybe n minus 1th to nth index, and new data has come, they will using that will be updating the norm square at that stage. So, at nth stage, norm square at the very first stage are obtained, and then you obtain for the at the same index from the 0th stage you obtain by the for the first stage, from first to second, second to third by a recursive formula. That is order recursion, but at the very first stage it has to be time recursion from n minus 1th to nth. As the new data has come, you have to modify the norm square in the 0th stage using the new data information. Once you obtain for that stage, then propagate it order recursively. Unfortunately, the same cannot be done for the top delta p n. You cannot get from delta p n to delta p plus 1 n to delta p plus 2 n, that is the problem. It cannot be done. It has to be time updated and it is far more complicated and more challenging. How to obtain delta p n plus 1 from delta p n? These are all beautiful linear algebra. We will do that. I do not think I have time today, so I will conclude. Thank you very much. It will take at least 2 days, 2 more days to complete the recursions. Okay, thanks.